Next, we're going to talk about what you can think of as a generalization of the belief propagation algorithm to graphs that are not trees. So we just talked about the belief propagation algorithm, and we said it was great in that it does inference very quickly on tree-structured Markov random fields. But of course, there's a big downside that it only works if you have a probabilistic graphical model that is specifically a tree-structured Markov random field. And we said that if we had a Bayesian network where even one variable has two parents, well, that will form a potential over that child plus its two parents. That will give you a cycle of length 3 in your Markov random field, and therefore you can't apply the belief propagation algorithm. So that seems not so useful. And in fact, the main reason we wanted to talk about it is as a lead up to the junction tree algorithm, which again you can think of as kind of a generalization of that algorithm, and works on any probabilistic graphical model, although the running time will depend on tree width. We'll talk about that in a minute. And the junction tree algorithm is used very often in practice. Here's the idea of the junction tree algorithm. Let's say we have some network that is not a tree that we would like to do inference over. So you can see that certainly this is not a tree. It has cycles everywhere. That's a cycle. That's a cycle. What we're going to do is we're going to produce something called a tree decomposition of this graph that is a tree, and where each node in this tree decomposition corresponds to a set of nodes in the original graph. So this node corresponds to the set ABC, and that's the set ABC in this graph here. And by the way, each node in the original graph can potentially occur multiple times in the tree decomposition. So this is the process of doing tree decomposition, and this we call a junction tree. Let's define this a little bit more precisely. So we say that a tree, or that a junction tree G prime is a tree decomposition of an original Markov random field G. If it's the case, there's going to be three properties. First, it has to be the case that for every variable x in G, that variable has to be associated with at least one node in G prime. So we can see we've done that here. For every node, for every variable in G, you can see that variable appears in at least one of our nodes in G prime. Second, it has to be the case that for every potential in G, where this potential is over some subset of nodes U. So recall that if we have a Markov random field, for every clique in G, we can have a potential that goes over the nodes in that clique. For every potential psi over that subset U, there has to be a node V in G prime such that U is a subset of V. That is to say that basically for every potential, that set of variables has to fit into one of our nodes. So you can see that this psi, we have a clique here, ABC, and a potential over that triplet, and we can see that that triplet appears in our node. We can check that for the other ones. Here's another triplet, DCE, and here we are, DCE. There's a node associated with that one. Needless to say, that works as well for pairs, so just two nodes connected with an edge, it has to be the case that those two nodes have to appear together in our junction tree. So G and H, we can see we have a node GH here. And if you like, this second rule sort of supersedes this rule, because recall that for a Markov random field, we can have individual potentials over each of our nodes. So if we had a potential over each one of our nodes, it would have to be the case that that potential could fit into one of our junction tree nodes. So by definition, all of our variables have to be represented. Third, the set of nodes in G' associated with some variable x has to form a subtree of G. Okay, so that is to say, for every variable in our original graph, let's take A, well, we said that it has to be associated with at least one node, so there has to be some subset of nodes in G' associated with A. Let's find those. That's these three here. It has to be the case that those three variables form a subtree in G'. That is, they have to all be connected, and there can't be any nodes that don't have A in between. So if we had some variable here, and this was over, let's say, DE, then that would violate this third property. An equivalent way of saying it is that for every pair of variables that includes A, it has to be the case that the path between those two variables, all the nodes along that path must also have A. So again, if we, for example, removed A from this node, then that would violate this third property. So this structure here, this junction tree, if we produce such a junction tree, it turns out that we can use it to apply the junction tree algorithm, which will give us an exact inference solution for whatever our inference question is about our Markov random field that we're given. So we'll talk about exactly how we do that in just a second. But first, let's talk about how we can produce such a junction tree in practice. Okay, let's say I hand you a Markov random field, and you want to turn it into a junction tree. That is, you want to find its tree decomposition. So, of course, one way to do it would be just to keep creating junction trees until you found one that satisfied all those properties. Of course, that would be very inefficient. So here's a algorithm you can use to find the tree decomposition. We're going to start with an ordering that we'll call pi. In this case, we'll use the ordering A, B, C, D, E, F, G, H. We're going to go through the variables in order, and we're going to take each variable, create a node in a junction graph that's associated with that variable. Not a junction tree yet. We're going to produce a junction graph, and then we'll talk about how to turn it into a junction tree in just a minute. But first, let's create our junction graph. By the way, we're going to go in reverse order in this ordering. That's how the textbook defines it. I don't know why it defines it that way, but we're just going to follow that. So we're going to start with H. Let's see what we're going to do for each variable. So we start with H. We're going to take each potential that H is involved in, and we're going to create a node involving all those variables. So in this case, H can be part of two potentials. It could be involved in a potential over just H, and it can be involved in potential over H and G. So we're going to create our variable GH, and then we're going to eliminate H from our graph. And we're going to go on to G. When we get to G, again, we're going to look at all the variables that G participates in potentials with. That's 3 variables, A, G, and F. So we're going to put those into a variable. And then we're also going to add in edges between all of the variables in that node. So we didn't have to do that for this node, but we're going to have to do this in this one because A and F were not connected in the original graph, but they are connected in this node. So we have to add this. This is called a fill-in edge. We do that to the original graph, and then in our junction graph, we're going to add an edge to all the variables that are all the nodes that share a variable with our new node, and we're going to number it with the number of shared variables. That's 1. Okay, then we're done with G. We're just going to keep going with this. Next one's F. F is involved with 2 variables, just with C in the original graph, but since we added the fill-in edge, it also is connected to A. So that gives us a node A, C, F. That shares 2 variables. We're done with F. We didn't have to add any fill-in edges, by the way. Next is E. We get a variable, or node, sorry, C, D, E. Done with E. Next is D. Notice that for D is connected to just one variable that's remaining in the graph. And note that we already have a node that includes that pair, C and D. So we're just gonna put any potential over C and D into this node that we have existing. We don't need to make a new node for D. So we're done with D. Now when we get to C, C is connected to these 3 variables, A, B, and C. So we're going to make a node for that. And note that it's connected to 1, 2, 3. Shares A with this one, A with this one, or sorry, A and C with this one, and C with this one. And we're done. Because notice that when we get to A and B, those are both incorporated in this node here. Okay, so that's our junction graph. We're going to turn it into a junction tree by taking the minimum spanning tree on this graph. There are multiple ways to produce the minimum spanning tree. Any of them are valid. So let's look at what the minimum spanning tree is. Sorry, not the minimum spanning tree, the maximum spanning tree. That is the spanning tree that has the maximum weight. So it's hopefully you remember what a spanning tree is. A spanning tree is a tree that incorporates all the nodes in the graph, but is a tree and uses a subset of the edges. So we're going to throw away some of these edges. We're going to end up with a tree, and that's going to be our junction tree. So it's pretty easy to see that for it to be a maximum spanning tree, it has to incorporate these 2 high weight edges. It's got to incorporate that edge because that's the only way to get to that variable there. This edge, well, we've already connected these 2 nodes, so we don't have to incorporate that one. And then we have a choice. We can incorporate either that edge or that edge. Both of them are the same weight, so both of them will leave us with a maximum spanning tree, and either one works. They're equivalent. Let's just pick this one for the sake of choosing one. Okay, and that's our junction tree. This thing here, minus these 2 edges, that's a junction tree. It is a valid junction tree. It's not the only junction tree we could produce. Note that we would get a different junction tree potentially if we use a different ordering on the variables. Our goal is generally to produce a junction tree with the smallest nodes. Our inference is going to scale according to the size of the largest node in our junction tree, and it's going to be exponential in the size of that maximum size node. So if we had even one node that had, for example, 10 variables, our inference would look like something to the 10th power because we have 10 variables in that node. In general, it's NP hard to figure out what is the best ordering for this algorithm, or more generally, to find the best tree decomposition. So it can take some trial and error or some intelligence to get a good tree decomposition for a particular graph. Let's do another example. We've seen this network before. We start with this Bayesian network regarding grades and job and life satisfaction, all that stuff. Recall that we converted it to a Markov random field by moralizing the coparents. So you can see, for example, this edge here came from moralizing these coparents there. Let's take this graph and find a tree decomposition for it. Okay, so here's our graph just blown up. We're going to use the ordering L, S, G, H, I, D, C, and recall that we're going to go in reverse order of the way I've written it, right to left in this order. I encourage you to pause the video and see what you get. So please pause. Okay, let's do our decomposition. We're going to move fast here. Okay, we've got C and D. Done with C. D, I, G. Do we need any fill-in edges? No, we don't. Done with D. I is next. We get I, G, S. I, G, S. Do we need any fill-in edges? No, still none. Do we need to connect across? No, we don't. Done with I. H is next. H goes to G and J. Let's draw this down here, H, G, J. Since it doesn't share any variables, do we need to draw any fill-ins? H, G, J, no we don't. G is next. We get G, S, L, J. Connected there. Fill-ins, none. Last is S, L, J. Oh, and that's it. And we had to connect that last one there. There we go. Okay, now let's just make sure we didn't mess up any connections. Okay, we also have this one, and we have to connect these two. No, we don't. Good. Okay, we've got to do our weights on our edges. I just saved this for the end. This is 1, 2, 2, 2, and 1. Hopefully I didn't miss any. I don't think I did. We need to get our maximum spanning tree. Pretty clear that we want to get rid of that edge, so we end up with this tree decomposition. Hopefully that's the same thing that you got. So we went to all that work to define a junction tree. Now, what good does it do us for inference? So it turns out it lets us define what we call the junction tree algorithm, which is the analogy to the belief propagation algorithm just in a junction tree. So how is that going to work? It turns out it's going to work exactly the same. We're not going to show the algorithm in its full formal definition, but I'm going to give you the idea. I encourage you to look at the book for the formal definition, but it's really almost identical to belief propagation, except that instead of using nodes where each node corresponds to a single variable, we're using nodes where each node corresponds to a set of variables. Okay, so the way this is going to work is for each edge corresponds to some subset of variables that are in common. So this edge corresponds to a C in common, a F, G, and C, respectively. So we're going to create messages where this is going to be a message from, let's number the nodes, 1, 2, 3, 4, 5, from node 1 to node 2, and that's going to be a message over the variables they have in common, A, comma, C. And likewise, we're going to create a message in the other direction, M from 2 to 1, over those same variables, A, comma, C. Those messages are going to be defined using the potentials associated with each node. Recall that there's that every potential in our network we put into one of these nodes in our junction tree. So you can think of each node as having kind of a set of potentials that's associated with it. Apart from that, everything's the same. I should say when we associate potentials with nodes, we need to make sure if one potential could fit in multiple nodes, we put it in just one node. So for example, if we had a potential over just G, that could go either in this node or this node, because both of them include G, but we're going to say that we only get to put each potential in one node, and we could put it, for example, in this one. Okay, then otherwise everything is exactly the same. We define our messages using those potentials in each variable. We send the messages using the messages we have in the other direction. By the way, we have to start from the leaves, same way we did for belief propagation. Using our messages coming in the other direction, we compute the messages that we send out to the leaves, and then if we want the distribution over some variable, we multiply together the potentials associated with that node times the messages going to that node. By the way, extra benefit is we can get probabilities not just for single nodes, but for any set of, not for single variables, but for any set of variables that share a node in the junction tree. Okay, so that's our junction tree algorithm. That is a very powerful algorithm, again, for exact inference. And again, realize that this works on any Markov random field, not just one that was already a tree. We basically took any MRF and put it into a junction tree such that we can run belief propagation on it. Note that our complexity of inference here, how expensive is it? Well, we have to do computation only over nodes in the same, only over variables in the same node. And for each node, we're going to end up producing a CPT, a factor, that's exponential in the number of variables in that node. So if every variable is binary, our CPT would be of size 2 to the k, where k is the size of that node, the size being the number of variables. And thus our inference cost is going to be proportional to the size of the largest node. So again, it's very important that we produce a junction tree such that no node is too large.